All right, guys, today we're going to look at differential equations. First of all, what is a differential equation? You can look at this top line here. The graph is nothing on this. I'm just using the Desmos to be able to type math a little better here. That's a differential equation. It's called a second order differential equation because it's got a second derivative in it. Basically, a differential equation is an equation that has unknowns like maybe x and y, but also one or more derivatives of, in this case, y in the equation. So this equation has an x, a y prime, and a y double prime, all kind of mixed together there. And a solution to a differential equation is something like the second line here, where it's an equation relating y and x directly to each other. In fact, the second line is a solution to this differential equation. Now, I'm not going to show you how to find this solution to this differential equation because this one's a little bit advanced. You might do this type of differential equation in a class called differential equations that you'll take in college if you major in math or engineering. But what we can do with this one is, since we are given the solution, one thing we can do is verify that it is indeed a solution. So we're going to do that. There is a type of differential equation that we are going to learn to solve. We'll probably start that tomorrow. But yeah, again, we'll wait on that. So first, how do I verify that the second line is in fact a solution to this differential equation up here? What I need to do is take the solution and find y prime and y double prime. Then I'm going to plug them in. I'm going to plug y prime, and y double prime all into the first line, and then show that it's true. So that's what we're going to do. So I'm going to go ahead and do the work on here, but you do it at your desk while I'm doing it. Just sit there, write down what y prime is, write down what y double prime is. I'll talk at some point. I'll try to not go too fast here so that you can do it as well. So I'm just going to go through and do derivative rules, right, from y here. That last term, think about what you have to do on that one. Right, I had chain rule on each of the first two terms. That last one is going to need product rule, right? So I've got my y prime up there. If you're still working on it, that's okay. I am going to combine like terms. I've got a minus 3e to the 3x and a plus 1e to the 3x. So here I'm just going to kind of take this, copy and paste. Minus 2e to the 3x and get rid of that term. Okay. So now I'm going to find y double prime from y prime. Got my y double prime there, and again, I'm going to combine like terms. Got this minus 6e to the 3x, and this plus 3e to the 3x, so that just makes a minus 3e to the 3x. Oops. Okay. So yeah, once we have that, we have y prime in line 4. I have y double prime in line 6. I have y in line 2. My next step is to just plug all three of those into line 1. And then I'm going to, do the work. You probably do it on pencil and paper. It's a little easier. And you're going to show that that makes a true statement. So I'm going to take this y double prime, because that's what my differential equation starts with, is y double prime. and minus 5y prime, so minus, and I can do 5 and then parentheses, all this stuff in line 4. I'm just going to go ahead and distribute as I go here. So minus, here, let me, well, yeah, I'm just going to copy and paste this. And what I'm going to do is I'm going to go ahead and distribute as I go here. So it's 5 times this, so it's going to be minus 10 e to the 2x. This is going to be plus because I'm distributing a negative. It's going to be 10 e to the 3x, and this is going to be minus 15 x e to the 3x. So that's the y prime line times 5, or negative 5, I guess. And then I've got the plus 6y, so 6 times all this stuff added on. So that's plus 6 e to the 2x minus 6 e to the 3x, 6x e to the 3x. Finally, that equals e to the 3x. The rest of the equation. It's a big, long, ugly differential equation. Graph's doing all kinds of crazy stuff. Like I said, we're not paying attention to the graph here, although it looks fun. And all I have to do now, it looks complicated, but all I have to do is combine like terms, and stuff should work out in a way that makes this clearly true, hopefully. So if you go ahead and combine like terms, I think you'll see that that's true. For example, the x e to the 3x terms have a negative 15, also have a plus 6x e to the 3x, and a plus 9x e to the 3x. So that does all add out to 0. It goes away. If you look at the e to the 2x terms, I have 4e to the 2x minus 10e to the 2x plus 6e to the 2x. That all adds out to 0. Now the e to the 3x terms, I have minus 3e to the 3x, I have plus 10e to the 3x, and I have minus 6e to the 3x. That does add up to 1e to the 3x. So the entire left side, combined like terms, it simplifies down to e to the 3x, and I get an identity. It's the same exact thing. So that's all we had to do. We verified that this is, in fact, a solution to this. Good. All right, so that's one of the things you want to be able to do. We're also going to talk right now about slope fields. So I have a slope field thing on Desmos, but I want to get to that. Let me start by showing you kind of from scratch how you can make a slope field. Actually, you know what? Let me show you a slope field first. So on Desmos, a slope field is like a graph of a differential equation. And if you imagine it to show, it shows a bunch of different solution curves at once. If you think about the thing we just looked at. So we had this differential equation here, and we had this solution here, right? Sometimes there's more than one solution to a differential equation. And in fact, generally there are. There's going to be more than one solution here. There's probably some places where we could have constants in here that are unspecified that would make it true. Think about when you do an antiderivative and you get a plus c, right? It creates infinitely many solutions because that c could be anything. So in this slope field, there's a bunch of different possible solution curves. And this shows kind of like all the different graphs. So this movable point here that I'm dragging around, if I picture this kind of going through the slope field, it would kind of follow along, like connect the dots here, and could create a solution curve like that. Or if it was over here, maybe it would kind of just do a solution curve that kind of goes down like that. Hard to kind of see it at first. You'll see some examples. But let's make our own slope field first and see if it makes any more sense. So here, I have a differential equation up here. Y prime equals x squared plus y. So what I'm going to do is make my own slope field. And it's just like going back to Algebra 1 when you were learning to graph a bunch of different stuff. What did you do? You took x values like -2, -1, 0, 1, and 2, and you plug them all into a function, and then you got points, and then you graph the points, right? You might use it to graph a line or an exponential function or something. So here we're going to do kind of the same thing, but we're going to do it with both x and y because my differential equation has y prime in terms of both x and y. So that's x squared plus y. So I'm going to plug all these different, I have 25 ordered pairs here in this table. All the x values from -2 to 2, or the integers, with the y value integers from -2 to 2. So for example, if I plug -2 in for both x and y, what do I get? Well, -2 squared is 4, and then plus y, which is also -2, that's going to be 2. For x is -1, that's -1 squared. So that's 1, plus -2 for y is -1. X equals 0. I'm just going to get -2 there. X equals 1, I'm going to get -1 again. And x equals 2, I'm going to get 2 again. You might notice some patterns when you're filling one of these out. For example, the x squared, when I plug in -2 and 2 for x, I'm going to get the same thing. When I plug in -1 and 1 for x, I'm going to get the same thing. So notice the symmetry here. I have 2 here and here. I have -1 here and here. So I'm going to have that in every row here, that same kind of symmetry. So it might make it a little easier if I notice that kind of stuff. So x is -2, that gives me 4 plus -1 for y, that's going to be it's going to be -1 plus 4 is 3. And you might notice right here, well, I'm just adding y to what I had for x squared. And this y is 1 greater than this y. So each of these values should be 1 greater than the thing above it. That doesn't make sense to you, go through and just evaluate it. Plug in the x and y ordered pair into this and make sure that you're getting the same values as me. But if you notice patterns that you can use, by all means, use them. So this is going to be 0 because it's 1 more than -1. This is going to be -1 because it's 1 more than -2, and so on. All right, I'm going to shut up now. I'm just going to go through and fill this out. You do it too, see if we get the same thing. Ready, I've got my answers up there. I could probably zoom in a little. Okay. And so these are slope values in the white 5x5 table in here. These are values of the slope of for this differential equation, x squared plus y, at all of these different xy ordered pairs. So what I could do now is I could go through and graph these on a plane. And again, this was x squared plus y. I'm going to go ahead and go to my slope field generator here and put that in. You can see what it looks like. Notice, forget about it for a second here. X squared plus y, let's just put that in. And if I just go from -2 to 2 here, now the way that these are in here, these aren't going at every integer for x. Notice this is at a little past 1 and a little past 2. Let me see if I can change that easily. Yeah. I'm going to go ahead and just change this to 1. There we go. Okay. And now this is a graph of that slope field. So I'm really just looking at the 25 hash marks here around 0. So from -2 for x and y up to 2 for x and y. So that part there that I'm kind of outlining. And this is just the graph of that table we just had. So for instance, at y equals 0, from -2 to 2 for x, we have 4, 1, 0, 1, and 4. So if I go back to my slope field, here's 4. This is a slope of 4. It's going like up 4 over 1. You can look at these little grid marks. They're not a full integer. They're like a fifth. If I followed this line, if I went up 1, 2, 3, 4, and went over 1, that's where it's pointing. right? So that's the slope of this line here. At -1, it was a slope of 1. When at like y equals 0, x equals -1. And this is a slope of 1, right? It's like going up 1 over 1. At 0, 0, it was 0. So that's a horizontal line slope there, and so on. So all of these are just little tiny line segments. I call them hash marks here, that show the slope of any solution curve to that differential equation as it passes through that point. Okay? We'll talk more about these. If it doesn't totally make sense today, that's okay. But that's what a slope field does. It's like a graph of a differential equation. It shows the slope, the dy dx, at various points in the xy plane for a first order differential equation. I hadn't mentioned that part yet, that it's a first order differential equation. In other words, the biggest derivative in the differential equation is going to be a first derivative if you're doing a slope field. Okay, slope fields really only are useful, or they only apply for a first order differential equation, as far as I know. Okay, so that's a slope field, and you can look in your text as well to see some more examples. In section 8.1, there are several different examples. We'll see some more tomorrow, but I'm going to give you guys some problems to do, and it includes sketching a solution curve on a slope field. All you're going to do when you're sketching a solution curve on a slope field is, it's like connect the dots. You're basically drawing the curve through the field and trying to kind of, as you pass through a point or near a point, have the same slope that point has. So you're going to be kind of curving with the little hash marks. Okay? So do the best you can with that. And I'm sorry that I'm not there today. It's a new topic, but I did not want to lose another day to me being out. So hopefully this is useful and workable here. All right, and I'll see you guys tomorrow. Do your best with these. Bye.